Okay, so the good news that I have for you is that there is an easier way to check these properties of being for a linear transformation being one-to-one and a linear transformation being onto. So first of all, let's look at this theorem, which is where we're going to see some details about that. So let's say you have a linear transformation T, and it's going to turn out to be useful to be able to reference its standard matrix. So let's say you've got a linear transformation T going from Rn to Rm, and it's got a standard matrix that's written like this. So you can see it's written as in terms of its columns. A1 is its first column, A2 is its second column, and so on all the way till its last column, AN. So that's what's set up in the background. So now we can make some statements. So the first statement is that this function t, this transformation t, is going to be one-to-one if and only if. Remember this if and only if? What that means is that this statement and this statement, the two statements that are linked by the if and only if, means they're equivalent. They're true under the exact same circumstances. So t is one-to-one exactly when the columns of its standard matrix, because that's where these vectors come from, the set containing those vectors is a linearly independent set of vectors. Okay, that's another way you can check whether t is one-to-one. So for example, in part B here, rather than doing all this work, right? Rather than doing this, what you may choose to do, since in this example in part A, you've already found the standard matrix of T, so you know that its columns are -1, 0, and 0, -1. This theorem is telling us that if we wanted to check whether T is one-to-one, all we need to do is check whether these two vectors are linearly independent. And you may find that that's less work than doing all of this. Okay, so that's an alternative that you have. You can just check if the columns of the standard matrix are linearly independent. Okay, and statement 2 is saying that T is onto exactly when the columns of the standard matrix, if you take the span of those vectors, you get all of Rm. In other words, every vector in Rm, the codomain, can be written as a linear combination of the columns of the standard matrix. That's really what statement number 2 is saying. It is equivalent to being onto if the span of your columns gives you all of the codomain Rm. Okay, and then 3 and 4 are just some little checks that you can do to save yourself some time when you're in this situation. So the first of these last two, so the third statement here, is if m is greater than n. So in other words, m is the dimension of your codomain and n is the dimension of your domain, right? So if your codomain is a higher dimensional space than your domain, then right away you know your transformation is not going to be onto, right? It is impossible to have a linear transformation from R2 to R3, for example, that is onto. It just will not happen. That's not true for functions, by the way. You can have a function from R2 to R3 that is onto, but you can't have a linear function from Rn to Rm, which is onto. Okay, so that's a useful check. So, for example, in this case, here we couldn't use that fact because our codomain was the same dimension as our domain. But if this had been a transformation from R7 to R8, for example, then the answer to C would immediately be no, without having to do any work. It is impossible to have T go from R to R from R5, say, to R6. If the dimension of your codomain is higher than the dimension of your domain, the function will never be onto. That's what statement 3 is saying. And then statement 4 is saying the other way around works for one-to-one. If the dimension of your domain is higher than the dimension of your codomain, then your transformation can never be one-to-one. So those are some tools that can save you some work.